Okay, so I was saying that we have to make sure that the set of instruments that we get are relevant and exogenous, and we just make an assumption and then we need to test this assumption. Okay, so before we go into the testing, let me first show you how to do the 2 stages. So stage number 1, what we need to do in stage 1 is that we're going to regress our endogenous variable, which is education, on the set of instruments I have. All the set of instruments I have, I'm going to be regressing my education against it. Okay, so let's okay, so education is a function of father education, alpha 2, mother education, plus everything else that is supposed to be exogenous. So we have alpha 3 experience plus alpha 4 experience squared plus the error term. So this is your stage number 1. You're taking your endogenous variable, you're regressing it on the 2 IVs that you have, and then the 2 exogenous variables that you have. For the relevance test, okay, you will need to check whether these 2 are, we said, correlated, but now I need to check their statistical significance, their combined effect. Okay, and this is what we are going to do next, which is we need to do a test here. Okay, out of this regression, you're going to get education hat. Okay, so what you need to do next is go to stage 2. And in stage 2, you're going to have, again, your main model. So your main model was log wage equal to lambda 0 plus lambda 1 education hat plus experience plus lambda 3 experience squared plus an error term. Okay, and this error term, just like I'm trying to write it nicely. Okay, and these coefficients are called the TSLS coefficients. And now when you try to think, okay, this is the test for relevance, because it makes sense that if I want to check whether these are, these are correlated with the education, then in the regression where I have education, I need to check their statistical significance. How about this one? How can I check this one? It makes sense to think about it that in the regression, let me write it on a different paper. In the regression, I need to extract the error term, right? And this error term is coming from the second stage regression, right? And after I get this error term, I'm going to regress it on the set of instruments. So I'm gonna, let's say, beta 0 plus beta 1, father education plus beta 2 mother education plus beta 3 experience plus beta 4 experience squared plus any VI, for example. And this is actually what you care about, the connection between these 2 and the error term. And you actually, like, oppositely to what we assumed in the previous test, is here now I want to make sure that beta 1 and beta 2 are not significant or are insignificant. So before I give you more details about these tests, let me first finish 2 important things, which are, one of them is the disadvantage, because we're going to spend so much time on the test. So this one is about the exogeneity test, and I'm going to spend so much time on this. So let me, before we spend time on this, I just want to talk about 2 points. One of the points is, what are the disadvantages of the IV method. And I'm sure that one of them actually was mentioned by Samantha last lecture, which is how can we find the IV? Like there are so many things. Like it's like you have multiple instruments that can work as an instrumental variable. So the first one is that we have many variables that we can use as IV. So you can think of it like, okay, that's good. Why not? Like if I have many variables that can work as an IV, like that's good, right? But the problem is, if I just leave everyone to choose, let's say we're in an exam and I'm giving you like a bunch of 10 instruments and I'm like leaving you to choose whatever you like, each one of you would get a different result. Like if you're using different IVs, you're getting different results. So this is a disadvantage. Like you cannot have a robust result using different instruments. No. So the problem is that the choice of one of them, like one of these instruments, you get different results. Okay, so you get different results. So you choose one of them, you get different results, choose another one, you get another result, and so on. Number two, when you try to think about variables that are correlated with X, then this number two is about the relevance of instruments. So it might not be that easy to get a variable that is strongly correlated with X. Okay, so it's not always, sometimes it's kind of difficult. Okay, so it is difficult to find IV such that it is strongly, because you want to have it strongly, right? Strongly, I'm sorry, my handwriting is crazy. That is strongly correlated with X or your endogenous variable. Okay, so
I have a question.
yes, sure.
When you say strongly correlated, like, are we talking about like, I don't know, a high value of the actual correlation, or what is the benchmark for?
That's a very good question, and we're gonna talk about the benchmark and the correlation right after this.
Okay.
Okay, so it's not actually some simple correlation, but it's a test, and we're gonna be talking about the benchmark. The other one is about the exogeneity. This is even a harder assumption, right? How can I make sure that the Z or the IV I use is totally independent from all other factors that are correlated with the dependent variable, right? So it's almost impossible, right? So it's almost impossible to check that the Z is, or the IV or the Z is independent of all UI or all the errors. Okay. The last disadvantage is something that we will discuss on Thursday, which is, you know, that every time we're discussing an instrumental, an econometric problem, we always discuss it in terms of, like, I want to write it here. You know, that T statistic has here, so beta hat, let's say beta hat 1 minus beta 1 beta 1 over the standard error of beta 1. So all the time we have like this ratio between the bias and efficiency, right? Because efficiency is represented by the variance, and the variance or the standard error are the same. So what you need to check is every time I'm using a different estimation methodology, I need to check how it affects consistency, which is the upper part of the T, biasness, which is the upper part of the T, efficiency, which is the lower part of the T. Some estimation methodologies, they would give more attention to one of the two, okay? So the IV regression gives more attention to the upper part. Okay, so it gives more attention, gives like or you can write it like IV gives priority to, I'm not gonna say the upper part, I'm going to say to consistency. So upper part of the T statistic is about consistency. Okay, and less attention to the lower part of the T statistic, which is the efficiency, right? And less attention to the possibility of high standard error, okay? So you usually have efficiency problem. So efficiency problem means that high standard error. So you can get like high standard error with the IV. Yes, the upper part of the T statistic is not a problem as much as the lower part of the T statistic where we have efficiency problem. So the variance of the estimator based on the IV regression will have a higher variance as compared to the estimator based on the OLS. Okay, so these are basically the main problems, okay? Of course, there are advantages. The advantages are the ones that we've been talking about since we started this topic, right? But these are the disadvantages that we should have in mind while using this estimation methodology. The second part I want to talk about is the IV regression assumptions. So every time we are talking about any estimation methodology, we have to talk about what are the assumptions and how and what's going to happen if these assumptions are violated. So again, like what's good here is that these assumptions are like relatively, if you already understand the OLS assumptions, the panel assumptions, these are exactly the same idea, but we are using it really for like the methodology of the IV. The first one, as you know, like we always have the first one related to the expectation of the error term, conditioned on W1I, W2I, W3I, WRI are equal to 0. So we said that these are, by definition, we call them exogenous. So this assumption is not like saying anything new, it's just confirming, okay? The variables that you call them exogenous are totally disconnected with the error term. And this is how we write it, okay? So this is number one. Number two, nothing new, right? Number two is again, nothing new. It's about the ID assumption, but we're going now to have multiple variables. We not only have the Y and the X, but we have Y and X and Ws, and we have also the Z's, right? So our set of variables, YI, our set of endogenous problematic variables that start from X1I all the way to XKI, and our set of exogenous non-problematic variables that start with W1I all the way to WRI, and our set of IVs that we are going to use that start with 1I all the way to CMI. All these are IID. So we're not going to spend more time talking about IID because we talked about it many times, but just expand the idea, the definitions that we discussed before to this assumption. Number three, no large outliers. And when I say no large outliers, you basically graph your variables and make sure that when you graph these variables, you don't have any variables that are outside the range of observations. When I say no large outliers, I'm talking about my dependent variable, no large outliers for the set of X's, no large outliers for the set of W's, no large outliers for the set of Z's. So all of them, I don't have any problem of non-constant variance arising from large outliers. Number 4, and this is something that we discussed. So the instruments, the IVs, okay? So when I say IVs, we named them Z1I all the way to Z2, ZMI, it's not 2, MI are valid. And when I say valid, we know already that validity is 2 things. They are relevant and they are exogenous. And this would brings us to the 2 tests that we need to perform, the relevance test and exogeneity test. Okay, so from here, we're gonna be talking about the last point, which is checking the instruments or the IV validity, right? So we have 2 tests that we need to talk about. So here we need to talk about validity test. And validity test is 2 things. So we need to talk about the relevance test. And I'm going to come to Daniela's question about the benchmark and the exogeneity test. Okay, so let's start with the first one. So with the first one, I kind of explained it, and it's relatively straightforward. So for the relevance test, it's all about the first stage F test. And I'm sure that you know what test I need to do. Like, so what you need to do is, I'm going to go to my first stage. So assume that my first stage is like this. Xi is equal to alpha naught plus alpha 1 Z1I plus alpha 2 Z2I plus an error term. Okay, so this is your first stage regression. Now, I want to check the relevance of the instruments. Okay, so when I need to check the relevance of the instruments, and actually let me expand this model so that in case you have W's, so you know that what you need to do. Okay, so I have alpha 3 W1 I plus alpha 4 W2 I plus UI. Now, again, relevance test is about disease. So my null hypothesis, and you know that I always ask you what is, write down your null hypothesis. Your null hypothesis is going to be whether alpha 1 is equal to 0 and alpha 2 is equal to 0, okay? And then your alternative hypothesis is one of the above does not hold, which is like typical of an F test. Alpha 1 is not equal to 0 and or alpha 2 is not equal to 0. Of course, in this test, you want to make sure that alpha 1 and alpha 2 are statistically significant, right? Because if they are statistically significant, then you're going to be say, okay, these are relevant instruments that can be used as IVs for the X, or I passed the first test. So if you get this, or you can think of your null hypothesis as saying that IV are not relevant or irrelevant, which is not good. This is a bad result, right? This one is saying IV are relevant. So actually you want to, you're hoping that you're hoping to reject the null, right? Because if I reject the null, then I'm going to say Z1I and Z2I are significant, right? Or significant, or statistically significant, or jointly statistically significant. In other words, you're gonna say Z1I and Z2I are relevant. Okay, so the idea is I want to get these instruments to be statistically significant. In terms of a benchmark, we actually need a benchmark, because it's not like just passing the critical value. No, I want this to be as high as possible. So there is one of the benchmarks suggested by a paper by Steger and Stock, and this was written in 1997. And this paper, they basically said that we need the F statistic of this test to be greater than 10. So it's not just like an F statistic that is passing the critical value. So suppose this is my critical value and this is the shaded region, right? I just don't want my F statistic to be right here. No, I want it to be as far as possible towards the tail of the distribution to make sure that I'm highly rejecting the null hypothesis. And they decided to put for us a certain benchmark. So this certain benchmark, again, is suggested by this paper. So if you want to go ahead and just read all the details, and this paper is very famous paper, and they are the ones who decided to put for us this benchmark, and we have more explanations on why 10 on this paper. Okay, so you get your F statistic of this regression. Suppose I get F statistic, and I'm just saying suppose, right? So suppose I get an F statistic that is equal to anything, 5. Okay, so we're gonna say if the first stage regression F stat is equal to 5, then IV are weak. When I say weak, you can say also irrelevant. So this is another word. I can say weak instruments, irrelevant instruments. Why? Because I need actually this number to be 10 or more. And that actually brings us to the idea of here when I was saying relevance, and I was saying, and back to Daniela's question, strongly correlated. So is it just a simple correlation? No, it's actually an F test, and not any F test. It's an F statistic that has a high value, and we need to pass not only the critical value, but also the number 10. So 10 or above, I should say. Okay. So this is for number 1, and I want to tell you that it's not that easy. And again, I keep remembering like what happened during my dissertation. I had a table, and this is usually what you do when you have an F test for multiple X's. If I have 5 X's, for example, in the model, I'm going to have 5 first stage F, because I'm going to have 5 regressions. And I want to tell you that you might have it, like the F test might be 10 in some of these regressions and might not be 10 for other regressions. So you have to make sure that it's 10 or above for all regressions, which is kind of challenging, right? And then if it doesn't pass the 10, then you go back and try to think about what are the possible instruments that I can use in my regression in order to maximize the correlation between the IVs and the endogenous variable. Any question? Okay, so let's go to the second test. So in the second test, which is, I the exogeneity test. How can we do that? I told you, like in the previous one, here, when we were using this one, I said it's the relevance test is about the first stage F test, okay? The exogeneity test depends on the second stage. It doesn't depend on the first stage. It depends on the second stage. Of course, the first and second stage are connected, but the specific test, the exogeneity test, depends on your output from the second stage. So remember, and I'm just want to let you to recall that you have in the second stage, I want you to recall the second stage. In the second stage, I have yi is regressed on, let's say, did I write alpha or whatever? Okay, let me write another thing. Beta naught plus beta 1 x 1 I hat, right? And I have two z's and I have w's. So I'm going to have here beta 2 z 1 I plus, beta 2 w1i plus beta 3 w2i plus vi. Okay, now I want you to get the error term of second stage regression. Okay, so you go and you get your error term, which is simply equal to yi minus yi hat. And I'm sure you know how to get that. But we're going to talk about how can we extract or how can we do these stages manually next time. So you get your error term, and this error term, we call it, because like to be more specific, the two-stage least squares error term. What you're going to do next is you're going to regress ui hat to SLS on delta naught plus delta 1 z1i plus delta 2 z2i plus the set of instruments, I mean like set of exogenous variables that you have, w1i okay, plus, let's call it anything, EI, okay? So you're going to do this regression. And if I'm trying to get a relevance, an exogeneity test, I want to make sure that delta 1 and delta 2 are not statistically significantly affecting the error term. So what you're going to do is, again, you're going to perform an F test. And this F test is on the delta 1 and delta 2. So your null hypothesis is going to be equal to whether delta 1 is equal, let me write it in a different way, delta 2 is equal to 0, okay, which is the same as writing it, just make more space here, okay, and the alternative hypothesis would be whether delta 1 and, sorry, it's not my day today. So delta 1 is not equal to 0 and or delta 2 is not equal to 0. Okay, or one of the above restrictions does not hold. And of course, you're hoping to be here. So if I'm here, you're gonna say, okay, IV are exogenous, which is good because I hope there is zero connection. If I'm here, IV are not exogenous, or you cannot use them. Okay, because they are still somehow connected with the error term, so you cannot use them. So you might actually be able to pass the relevance test, but when you come to the exogeneity test, you cannot pass the exogeneity test. So what you're going to do is just go back, choose another set of instruments. So this is actually called the second stage F statistic, right? There is a certain test that is used, which is called the J statistic. And
can I ask you a quick question?
Yes, sure.
So we have to pass both tests?
Mm-hmm.
Thank you.
Mm-hmm. Yes. So, and remember at the beginning of this topic, I said it's always and, so it has to be relevant and exogenous. So you have to pass both tests. Okay. So the J statistic is computed in this test, and the J statistic is simply equal to the F test that you get. So it's going to be like the number of instruments times the second stage F statistic. Okay, and this J statistic is distributed as a chi-squared with M, which is the number of instruments you have, minus K, which is the number of X's you have, degrees of freedom. Okay, so this one is the second stage F. So I want you to imagine it like this. In the second stage, it's again an F test, right? And if I'm here, if I'm the shaded region, then IVs are not exogenous, okay? Which is bad. I want to be here in this white region, okay? So here are IVs are exogenous, okay? So IV are, so I want to be in this white region, but it's not only any F. Remember, you want to make sure that this J statistic, which is equal how many instruments you have, and what is the second stage F statistic. You multiply these two together, okay? So these are multiplication. And then whatever you get, so this is, you're going to compare with a chi-square distribution with M minus K degrees of freedom. So for example, suppose I have two IVs and I have one endogenous, which is like our example, okay? I have two Z's and I have one X. So here I have M is equal to 2, which is the number of instruments. I have one X, so K is equal to 1. So that means chi-square is distributed as 2 minus 1, M minus K. So if you go and check, which is chi-square with 1 degrees of freedom. So if you go and check your chi-square table, you choose any percent, like any significance level you like. Let's say I'm using at the 5%, okay? This is just I decided to use it at the 5%. You're going to find this number as 3.84. So your critical value here is 3.84. So you want to make sure that this J statistic is any value that is below 3.84, so that you can say that my instruments are exogenous. Okay, so it's not like a straightforward F test, although it can be used in some cases, just straightforward F test, and I'm going to tell you when. But in this case, whenever I have number of instruments are greater than the number of endogenous variables, 2 is greater than 1, M is greater than K, I'm going to be using the J statistic. Okay, so I need to make sure that this J statistic is below the critical value of 3.84. I want you to understand that this J statistic is, in some textbooks, is called the over-identification test. So you can say exogeneity test or over-identification test. When can I call it over-identification test? I can call it over-identification test if I have an over-identified model. Can anyone remember what is an over-identified model? Anyone? We said it last week. It's all about the comparison, not last week, Tuesday. It's all about the comparison between M and K. If the M is greater than K, like here, M is greater than K, we call it over-identified model. and you can call it over identification test. Okay, so whenever m is greater than k, then it's over identified model over identification test, and you can use the J statistic. So the J statistic can only be used anytime I have an over identified model. It cannot be used if I have exactly identified. Okay, if the number of instruments are exactly equal to the number of endogenous variables, I cannot use the J statistic. In this situation, you will be just depending on the F test. Okay, so you take the F test, you check the critical value, and again, you hope to be in the acceptance region or the non-rejection region so that you can say my instruments are exogenous. Okay, so any question? Does anyone have any question?
Hi, Professor. I have a question about the relevance test.
Mm-hmm.
I just want to know that if you only have one endogenous variable and you only have one instrument, so how can you do the F test?
Yeah, that's a good question. So in this situation, you just depend on the T statistic. Okay. So,
okay.
yeah, it's going to be like a regular T statistic. It's an exactly identified model, right? So in this situation, you just look at the T statistic. You don't have a benchmark in this case. It's just, when we say the benchmark is 10 when I have more than one instrument. Okay. It's always recommended to use more than one instrument. It's always recommended to have an over-identified model. Okay, but for your question, then just you look at the T statistic. And remember the F statistic for two variables, let's say, it's made out of the average of the square term of the T statistic of each coefficient. So implicitly saying that F is a reflection of the T. But if I just have one, then just look at the T statistic of this variable.
Okay, thank you.
Any other question? Okay, so what we're gonna do next? Okay, so let me talk about the estimation. So in order to estimate the model, I said like we have two stages, right? Let me show you in Stata how can you estimate the model. And on this Friday recitation, we have new materials for the recitation. It's all about the IV regression model. So let's see how we can estimate it in Stata. So if I'm trying to do the two stages, okay, two stages, least square. So if I'm trying to do the two stages least square, stage one would be like this. And again, suppose I have 1x, 2 z's, 2 w's. And suppose it's a robust, we're using a robust standard error because of heteroscedasticity. It's just an assumption. So if I'm going to do the first regression, the first stage is going to be like to regress x, z1, z2, w1, w2. And if I'm using, I can use also robust standard error, or you don't have to, but let's assume that we have heteroscedasticity, so we need to use a robust standard error. Okay, now I want to get my x hat, so predict. Let me call it, you call it anything you like, you can call it your name, but I'm gonna call it x hat, and fitted. Okay, and then in stage two, now we got x hat, we're gonna use it in stage two, and it's gonna be like regress y, x hat, w1, w2, robust. And now the output of this regression are the output of two stage least square coefficients, and that's it. Okay, so here what we did is assuming that the z's are the correct ones to be used, then we are actually able to estimate the model. There is another option, which is, so I want you to or I usually call this like estimating like step by step, right? So I want you to see how we can use it. Can we estimate it?
Can you go back to the slide real quick?
We have another option. Let me say this is option 1. So option 1 is a step by step. Like, how can I estimate this model manually without asking Stata to estimate it for me? Okay, so this is one option, and you have to learn like both options, because I might ask you to do it manually, or I might ask you to just do it as all at once approach. Okay, Samantha, you done?
Yes, thank you.
So the second option is, let me call it option 2, is doing this IV analysis all at once. How can I do that? In Stata, we have actually a command. It's IV reg 2SLS, and you write it this way. And then you tell Stata what is your dependent variable. It's Y. You write any exogenous variables next to the Y, W1, W2, and any problematic variable in between brackets. So I have one endogenous X that has instruments Z1, Z2, and you close the bracket, and then comma, robust. So this way you're telling Stata that, okay, estimate for me all at once. I don't have to do it manually, like in 2 steps as I just showed you. You can do it this way: IV reg 2SLS Y set of exogenous variables, and then between brackets your endogenous variable equal the 2 instruments that you have, that you will be using, and then the robust standard error. There are important things to note. So I want to make sure that you notice that, and you're going to see it on Fridays and Monday recitation. Number 1, if you do it like option 1 or option 2, your betas, your estimators are exactly going to be the same, exactly same numbers, which is good, right? So estimates of coefficients, or I'm gonna call them betas. I don't have to call them betas because I kept using different notations, but you understand. So the estimates of coefficients for option 1 and 2 are the same, exactly the same. So this is good news, right? However, I want you to notice that if you check the second column, which is the standard error of the coefficients, the standard errors of the coefficients are not the same, okay? So the standard errors of option 2 are larger, okay? Why are they larger? Because actually when you estimate the all at once, which is option 2, Stata in the background is computing for you the new standard errors. However, if I do it manually here, like here, when I'm doing it manually, the standard errors that are estimated here in option 2, I mean in option 1, which are the OLS, they actually fail to adjust for the fact that the stage 2 or the second stage regression use the predicted values of the included endogenous variable. So I want to kind of explain it in details. So where is my notes? Oh my God. Okay, here. Okay, I have an empty slide in between. So the standard error of option 2, larger. And I'm going to explain this in the next lecture. I'm going to show you in details how the standard error of option 2 is computed, how the standard error of the OLS, which I assume you know already, is computed. And I'm going to put the two together and show you that they are different. This is the correct one. Okay, so the standard error that you get from all at once is the correct one. I can actually make the correction for this regression. And I'm going to show you that we can make a correction here, despite the fact it looks like easy, right? Step 1 and step 2, but the standard error computed here are not correct. Why? Because I need to go and do some modification of the computation of the standard error, because the standard error computed here is assuming that I'm just doing an OLS regression. So I'm going to show you how can I override it's not an override, how can I modify the standard error to match the standard error computed here. Okay, and that's why, like, usually whenever I'm in an exam, or I'm asking you to use an IV without specifying which method to use, then you go ahead and use this one because it has the correct standard error and it's a shortcut, right? You just one step, one sentence. In the option 1 is like 2 steps, and then in step 2 you need to correct the standard error by following the steps that I'm going to be showing to you in the next lecture, because otherwise the OLS failed to adjust for the fact that the second stage is using the predicted value of X. Okay, also there is good news, which is here. Can I erase this? Because instead of writing this regression again, so let me write it here. So I want you to know that you can actually perform your first stage regression, your relevance test and exogeneity test right after this sentence. So after this sentence, you can do the state first stage, and in the state first stage, it's actually going to get you the first stage F statistic. You don't have to compute it by hand. It's going to be like right there. Okay, and let me just correct one thing because it's missing the first stage. Okay, one word. Okay, so this would give you the relevance test. So it would give you the F statistic, and all that you need to do is to compare it with number 10, and hopefully it's 10 or more. Okay, so that you can be sure that your instruments are relevant. You can also do the over identification test, state over ID, and the state over ID is the exogeneity test. And to be more specific, here I have the number of instruments, M, is greater than K. It's an over-identified model. So to be more specific, we're gonna call it over-identification test. So either you can call it exogeneity test, it's a general name for this specific test, but now I have M is greater than K, I'm going to call it over-identification test. And the over-identification test is going to be to give you the J statistic, right? All what you need to do here is take this J statistic and you compare it with the chi-square, M minus K degrees of freedom. So the advantage of option 2 is that you get everything you need, right? You estimate your model, you get the correct estimators, you get the correct standard error. You can just, in 2 lines, get your relevance test, get your exogeneity test, or more specifically, over-identification test, okay? So it's easy. And I'm sure that you know that we can do this one manually, right? You can get X regressed on the Z's and the W's, and then you check the F statistic by test PARM. I'm sure that you know that you can do this manually. You can extract the F statistic, you can multiply it times 2, which is the number of instruments here, and then you can compute your J statistic. And I'm going to show you this on Thursday. So I'm going to show you how can I do these two manually if I'm going with option, where is it? Option 1. So in option 1, which is a step-by-step, I did these two. I know that this one is not the correct standard error, but I'm going to show you how to correct it. And also I'm going to show you how can you do the first stage regression, the relevance test and the exogeneity test manually. Okay, any question? Okay. So we have what? Okay, we have 2 more minutes. You know what? I can show you one of the tests. So since I'm here on this slide, how can I do the relevance test? Relevance test is all about stage 1. So here, what I'm gonna do is I do the regression, and then I'm going to do right under here test PARM Z1 Z2. You're done. This one would get you the F statistic. And then all what you need to do is make sure that it's 10 or more. So this is manually how can I do the relevance test. Okay. For the exogeneity test, it's based on the second stage regression, right? So all what you need to do is first of all, you need to get your F statistic and then multiply it, right? So let me just erase this part. So I'm not gonna show you everything because it's kind of a long command, but I'm going to show you a part of it. So this is, we said that this is the relevance test. Now the exogeneity test. We're going to get the error term of this regression. So we're gonna say predict, right? I'm gonna call it residual and residue, okay? Or let me call it error so that you're not confused, because this part you can name it whatever. Okay, I'm gonna call it error so that you're not confused. And this one, you have to write it this way. And then what you need to do next is I'm going to regress my error term on the set of instruments and the set of W's that we have. Next, what you need to do is just, again, same. Get the F statistics. So test PARM Z1 Z2, okay? And then after you're done, you need to extract this F because I need to create a scalar, and I'm gonna call it J statistic that is equal to, you know that F is stored in this vector, which is R, F, and then you multiply it times 2, okay? Now you get your F times 2. You can also get your p-value, and I know we're almost done. I'm going to just write this 2 lines. P-value using the chi square. So you write it as chi, C-H-I, probability. This way theta would understand. M minus K, I have it as 1. And then you're typing J, so theta would understand that you want to get the J statistic, and that's it. You can also be like make a nice presentation, like you can present your results nicely and by displaying commands. So you can say, okay, display J, display its p-value, and that's it. So you get the J statistic, you get its p-value, you can compare this with the chi-square with m minus k degrees of freedom, and you're done. And again, you hope that this number is hopefully below this chi-square so that you can say my instruments are exogenous. All right, so we're gonna stop here, and we're gonna continue on Thursday. On Thursday, I'm gonna show it to you on Stata, and we're going to be talking about a couple of examples. And on Friday, you will see the application during the recitation time. All right, if you have any question, I'll available during office hours or on the discussion forum. All right, enjoy the rest of your day. Thank you. Thank you.
Thank you, Professor.
Thank you, Hamid. Thank you.